Hey everyone, and welcome to The Explainer. I am so thrilled you're here today because we're taking a deep dive into a fascinating and honestly somewhat hidden world. When we talk about microchips, we almost always focus on the front end, that crazy nanoscale printing happening inside those massive multi-billion-dollar clean rooms. But that's actually only the beginning of the story. Today, we're looking at the crucial final steps. We're going to explore the last mile of the microchip by going inside semiconductor back-end manufacturing. Okay, let's dive into this. Here is our chronological roadmap for today. 1. The chip's last mile. 2. First pass chip probing. 3. The physical journey. 4. The final exam, FT. 5. The traceability challenge. And 6. The 3D packaging revolution. All right, starting us off with section 1, the chip's last mile, front end versus back end. So to get our bearings, think of the front-end fab as the construction crew that's basically building the house. They're using incredibly complex, mind-bending processes to print nanocircuits onto a giant silicon wafer. But once that wafer passes a basic health check, it's handed off to the back-end facility, often called an OSAT. The back-end is entirely responsible for the interior decorating and quality control. They take that raw structure, package it up so it can actually plug into a real-world circuit board, and then rigorously test it to make absolutely sure it functions perfectly. Moving right along to section 2, first pass chip probing, testing before cutting. During chip probing, or what's commonly called CP, they use a specialized device called a probe card. This thing has these microscopic hair-thin needles that physically touch the testing pads on the uncut wafer. Now, why go through all this effort before even cutting the wafer? Well, it all comes down to cost control. Packaging a chip costs real money, right? So by screening out the bad dies right now, the factory saves an absolute fortune by simply ignoring those dead chips during the next steps. But just as importantly, CP provides critical process feedback. By seeing exactly which chips failed, the design team gets vital clues to fix upstream manufacturing issues. And it's pretty interesting. The testing volume here is actually a dynamic decision. If a process is highly mature, say with a 99.9% yield, they might just sample test a few spots. But if it's a brand new chip, oh yeah, they're testing every single one. The ultimate result of all this probing is a wafer map. Imagine a digital health check map for the silicon. Every single die gets assigned a bin code. A good, perfectly working die gets categorized as bin 1. Picture that as a vibrant, healthy green. Failures get categorized into other bins, painted in high contrast red or yellow, depending on the specific type of failure, like maybe a short circuit or a power leak. It's incredibly visual. If you see a whole cluster of red on the edge of the wafer map, the factory instantly knows something went physically wrong with how the wafer was processed on its edges. That takes us to section 3, the physical journey, from wafer to packaged IC. So how does this physical transformation actually happen? First, the wafer is thinned down, and I mean really thinned down to help with heat dissipation and just the overall size of the device. Because it becomes so fragile, they apply a blue support film to literally hold the whole thing together. Then, a diamond saw slices the wafer into individual squares, which we call dies. The robotic machines look at our wafer map, completely skip over those bad red dies, and pick up only the good green ones, gluing them down in a step called die attach. Right after that comes wire bonding. They use ultra-fine gold or copper wire to connect the die to the frame. The precision here is just astonishing. It's quite literally like embroidering on a grain of rice. And finally, the whole shebang is encased in plastic molding to protect those super fragile wires. That is what gives us the familiar black square chip we all recognize. Now, what's really interesting about this whole process is that it raises a pretty massive question. We just spent all that time, effort, and money probing the wafer back in step 1. So why on earth do we need another round of testing? Which brings us nicely to section 4, the final exam, FT, or final test. Well, to answer that previous question, the packaging process is violently physical. Slicing with a literal diamond saw, applying high heat, injecting liquid plastic, all of this can easily damage the chip or snap one of those tiny embroidered wires. So FT is there to catch these brand new defects. Plus, while the initial probe just checks basic health, FT tests the complete electrical specs. It pushes the chip's speed to the limit, monitors its power consumption, and simulates harsh real-world environments like extreme hot or cold temperatures. It acts as the ultimate quality gatekeeper before the product actually goes into your phone or computer. All right, section 5, the traceability challenge, tracking the lost dies. Remember that beautiful color-coded wafer map we talked about a few minutes ago? Well, here is the huge catch. Once that diamond saw slices the wafer and the dies are plucked off and glued into frames, they completely lose their original X and Y coordinate data. They become a totally scrambled mix of independent ICs. So if a chip fails the final test, sure, we know it's dead, but we have absolutely no idea where it originally sat on the source wafer. To solve this major headache, modern factories are implementing die-level tracking. By laser engraving microscopic IDs right onto the silicon, or by using some seriously advanced image recognition databases, manufacturers can now scan a fully packaged IC and trace it all the way back to its exact original coordinate on the source wafer. This is a real game changer. It turns the final test from a simple pass-or-fail checkpoint into an incredibly powerful diagnostic tool. Suddenly, you can cross-reference a final failure with the original wafer map to find the exact root cause of the problem. And finally, Section 6, the 3D packaging revolution, stacking the future. And this brilliantly illustrates the massive shift happening in the industry right now. Think of it this way. Traditional wire bonding is kind of like taking the stairs. You have to route signals all the way out to the edge of the chip, down along external wire, and over to the next component. It inherently causes signal delay and eats up more power. But modern 3D packaging, which uses a technology called TSV, is like taking the elevator. They literally drill vertical shafts directly through the silicon floors. This creates ultra-short data paths with incredibly high connection density. This elevator concept is the foundation of super advanced packaging technologies like CoWoS, which stands for chip on wafer on substrate. Let's break down that jargon real quick. Instead of a normal green plastic circuit board, CoWoS uses a silicone interposer. Think of it as a super precision mini circuit board made of actual silicone, which allows for microscopic wiring. Different chips, like a massive AI processor and its memory banks, are stacked onto this interposer using incredibly dense microbumps instead of those old long wires. And inside these chips are those TSV elevator shafts we just mentioned, firing data vertically at lightning speeds. It's essentially stacking chips like high-tech Legos to achieve massive, unprecedented bandwidth. But here is where the stakes get astronomically high. When you package multiple high-end chips together, say a cutting-edge GPU from one company and high-bandwidth memory from another, a single bad die or even the tiniest assembly error can ruin the entire integrated module. We aren't talking about throwing away a $5 chip here. We are talking about scrapping AI hardware worth tens, sometimes hundreds of thousands of dollars for a single unit. Because of the insane costs associated with these 3D packages, the reality of the industry today is perfectly summed up right here. Die-level tracking is no longer a bonus. It's a necessary standard equipment in the multi-chip AI era. If a CoWoS module fails, you absolutely must be able to trace exactly which chip from which supplier failed. Otherwise, you're going to be eating a massive financial loss without any clue how to fix the manufacturing flaw for the next batch. So from probing the raw wafer to the delicate art of wire bonding, all the way to the massive data challenge of tracking every single piece of silicon inside a 3D AI superchip, the back end is just as insanely innovative as the front end. And it leaves us with a really provocative thought. As we continue to stack chips higher, tighter, and smarter to fuel the AI revolution, what invisible manufacturing barriers are we going to need to break next? Definitely something to think about the next time you use your ultra-fast smartphone or computer. Thank you so much for joining me on this explainer today. I really hope it brought this complex topic into sharp focus for you. Keep learning, and I'll catch you on the next one.